Hey, this is Dino, and I have something interesting for you. If you care about denial of service attacks and you'd like to have more tools in your toolbox for countering denial of service attacks, I want to talk to you about proof of work algorithms, and specifically, we'll talk about Hashcash. Hashcash is a proof of work algorithm that has been used effectively as a denial of service countermeasure. The way it works is a receiver of a message places a requirement on the sender of the message that they must perform some work before sending a valid message. So when the receiver receives the message, they can verify that the sender did some computationally expensive amount of work before treating the message as valid. And verifying that the work has been done is a low-cost operation, whereas the actual work that needs to be done by the sender is a computationally more expensive operation. So the entire idea is that if we can force the clients to perform some computationally expensive work, it makes bots much less practical. And Hashcash has been around for a long time, more than a decade. It is widely used in Bitcoin. However, it is not limited to use within Bitcoin. Tearing open the hood a little bit, the main idea is that the receiver of a Hashcash stamp gets to stipulate the number of leading zeros that a hash on a string must exhibit. And if you know anything about hashes, they're one way, and so it's very difficult to do that. Basically, there's no way around it. The client must compute lots and lots of hashes and try to find one that has lots of leading zeros. That's going to take some time. Sending that string over to the server to say, okay, this is the string that will produce a hash with leading zeros. The server can then verify that very easily. It doesn't have to go through a whole lot of work. So it means the client does a bunch of work, the server doesn't have to, just to verify that the client did that work. And this is the way that we discourage bots. So Hashcash is the implementation. It has been used in Bitcoin. It has been used in email. We're going to show how to use it in API Proxies. By the way, if you want to learn more about it, you can look on Wikipedia. You can go to hashcash.org, where that's the homepage, but also Wikipedia has a nice technical article that describes how it works, including what the sender has to do, what the receiver has to do, and how all the pieces work. And the code that I'm going to demonstrate for you today is available on GitHub. And you can grab this and put this in your own API proxy and use it today. So let's have a look. I've got a directory where I've cloned that repo. First thing I want to do is build the code. So what I'll do is I'll run Maven here. And I've got three different sub-projects here. One is the Hashcash library. One is the callout that is used within Apigee Edge that depends on that library. And then finally, there's a tool that also uses the library just for use on the client side for demonstration. So I ran that. You can see the build took about 10 seconds, so we're good. We're in good shape here. Now that I've got the thing built, I can provision this into my organization using a script that is also included in the repo. So I'll specify my organization, that's the name of it, and specify my credentials. And what this is now doing, this script is running curl commands that use the Apigee Edge Administrative API to provision the API proxy and to import it and to deploy it. So it is now deployed. And if I flip over to my my user interface for Apigee Edge, you'll see there is the API proxy, and it is deployed. And we can have a look at the policies that are there and the flows that are there and so on. So very simple. The kind of interesting part of it is the Java callout that accepts an input hash and then the number of bits that need to be 0 in that hash. This is the requirement that the receiver is putting on the sender, or in our case, the API publisher is putting on the API client. So this might be 20 bits, it might be 22 bits. You can turn that knob up and down depending on how much work you want to force the client to do, but it's as simple as that. to verify a hash cache in Apigee Edge. So let's have a look at this thing in practice. Let me flip back to my command line. So I've deployed the API proxy. Now what I need to do is invoke it. And the way I'm going to do that is just with the curl command. But before I do that, I need a hash cache. So I'm going to have to generate one. And there actually is a tool also included here that allows me to generate that. So let's run that with a couple of different options. We'll run it with in Hashcash. There is a resource string, which I'm putting here. It's just an email address in this case, but you could use a client ID. You can use whatever you want, and then a bit strength. So I'll say 20 bits in the leading zeros for the resulting hash. And what this tool is going to do is run for a little while and then come up with a hash cache that has a timestamp on it, the resource string, and then the additional data that is required in order to get the leading zeros when you SHA-1 hash it. And I want to show you something. If I crank this up to 22, it's going to take a little longer. And this is running in real time. So what you'll see is it's exponential time for every additional bit that I need to be 0. It takes that much longer. If I turn this up to 24, it'll take a lot longer. If I turn it to 32, it could take several weeks to compute. So that's probably too much. But in any case, that's what a hash cache looks like. And if I then send that up to the client, send that up to the API proxy, the API proxy can perform the SHA check on it and verify the leading zeros are whatever they want them to be. And that's how Hashcash works. So how are we going to invoke the API proxy? We'll use curl. And in my case, it's going to be a post. I need the content type to be application JSON for this example API proxy. And I'm going to specify my organization. And the proxy is listening there, and we want verify no resource. The payload is going to be a JSON payload. So I'll say the hash. I need the hash, and I'm going to put this value in. And we'll pass that in. And then also one other property, the bits strength. And now the client, I'm the client here, and I'm passing in the bit strength. Normally you wouldn't do that with a Hashcash implementation. The server stipulates the bit strength, but just for demonstration purposes, I'm going to show you how the client can pass in a value, and Apigee Edge will use that to enforce. So we'll say the required bit strength on this is 20. And as you can see, I computed it with 22 leading zeros, so this should be valid. Let's see what happens. We're going to invoke that. And what's it saying? Well, we're getting a response output. And again, this is a contrived response just for purposes of demonstration, but it's saying this is the hash that I looked at. The required bits you told me were 20. The actual bits that were sent in on that hash were 22. Is it valid? No, it's not. Why is that? Because the timestamp check failed. And that is to say this timestamp, which was embedded in the hash cache, it was more than a minute old. So the time allowance, I configured the policy to have 60-second time allowance, and it was actually almost 2 minutes. So the time delta was too high, and the Apigee Edge policy rejected that hash cache. So I'll tell you what we'll do is we'll create another one, and we'll run that same command. I won't. I'll just copy this in. I have 60 seconds to be able to copy it, and then produce another command that has what I want in terms of the hash. So I'll send that in, and sure enough, that's going to say, yep, it's valid. That hash cache is valid. The client has demonstrated that by sending in this hash, the client has demonstrated that they did a bunch of work to find a string that has leading zeros in the SHA-1 hash. So what happens if I modify that hash? What if I just change one bit? So this is an F. Let's change it to an E, and we'll send that in. What Apigee Edge is going to do is compute that hash and say, I didn't see a bunch of leading zeros on that hash because this didn't work out. The hash that I computed does not exhibit 20 leading zeros. We really only had one leading zero, and so that's insufficient. And that's why that's why these things cannot be forged. A Hashcash stamp cannot be forged. It has to be computed, and that takes time on the client side. So let's see, what else could we do? What else can I show you? Let's generate another one. We need to get a fresh one because time has been elapsing. And I'll copy that. It's a new, because it's got a new timestamp, it needs to have a new suffix. And then we'll pass that one in, and we'll require the bits to be, let's say, 32. So we know this is a valid hash cache. We know it's probably going to have at least 22 leading zeros in the SHA. And in fact, it had 23. But because the policy was requiring 32, again, it's insufficient. So this is a way that you can include this proof of work requirement in any API proxy. Just drop in this Java callout, verify Hashcash, and then you'll be able to see whether the client has actually performed the work that you're requiring of him or not. While it can take the client hundreds of milliseconds in order to produce the string that hashes in the correct way, you can see in my Apigee Edge organization, it's taking just a few milliseconds to verify that SHA and that it has the required leading zero bits. So very fast to verify at runtime. So that's Hashcash in Apigee Edge. And I want to remind you that all the code and the provisioning scripts are available up in GitHub. By the way, when you're finished using this example, you can tear it down by using the same provisioning script. Just add a -r to the provisioning script, and what it will do is undeploy the API proxy and delete it, so your environment is clean and there's nothing left lying around. All right, hope this was helpful. Check back again for more interesting stuff on Apigee Community.